So the task for this video is to choose a point randomly inside of this circle without doing the lame method of choosing from a uniform x and y and then excluding any points outside of the circle. That's lame. Uh, so let's talk about this in terms of area. If I draw a circle within this bigger circle, if I can even draw a circle, that's, sorry, this just becomes a circle drawing exercise. Pretend that's a perfect circle, and that it's centered on 0. Um, let's say that the area of this circle is 0.5, even though clearly, uh, by 0.5 I mean like, let's say the total area of this whole circle is 1, even though it's not. It's like pi times, it's pi. But let's just say that this is a total circle is 1, and this smaller circle is 0.5. Then we would want the probability of choosing a random point in this smaller circle to be, 50%, a half. And this smaller circle, if we were to choose a point in this smaller circle, then that point that we would choose would have a radius, some radius. We could also say that it would have an x and a y, but for what we're doing here, I'm going to be using radius and like angle or theta or whatever. So that point would have a radius and then an angle around the circle. Um, oh yeah, okay. So when the radius is whatever this radius is, we want it to have probability of 0.5 of choosing a circle in this circle, in this smaller circle. And every point that is in this smaller circle has a radius that is less than the radius of this smaller circle. So you could say that the cumulative probability of you choosing this radius should be 0.5. By cumulative probability, I mean probability of choosing a smaller radius or this radius. The probability of choosing a radius that is, you know, this radius or this radius or this radius or this radius. The total probability of choosing any of those should be 0.5. And the total probability of choosing any of these radii as well should be 1, because that's, it's the whole big circle. And choosing this one should be, have an even smaller probability than 0.5. It's like a cumulative probability. And we want the cumulative probability to be the proportion of this area of the circle to the area of the whole circle. So if this area is 0.5 and the whole area is 1, then the cumulative probability should be 0.5. And so the general formula for that is the area of the smaller circle here. Does that pick up on the stupid cars driving by? The area of the smaller circle over the area of the bigger circle, which is a constant. And that simplifies to just being r squared. Uh, so the cumulative, let's say that I'm thinking of a radius of 0.5. The cumulative probability of me choosing a radius of 0.5 should be 0.25. And that makes sense because this area, I said it was 0.5 earlier, but this area is actually about a quarter of the area of the whole circle. And that's this radius, which is 0.5 squared. So that kind of tracks. All right. What next? I should graph this. This is the cumulative, that's why it's C. That's why I chose C. Cumulative probability given the radius. Um, and that just looks like this. It's just x, r squared. Okay. And what's the next step here? Oh, yeah, so, okay. So this is a cumulative distribution function, which is good because it gives us the probability of less than or equal to r being chosen. But what if we want the individual likelihood of a specific radius being chosen? Um, then we would take the uh, derivative. I'm not sure what's right here. Whatever. So this is the cumulative density function, and we would take the derivative of this x squared to get the uh, uh, probability density function. Did I say cumulative density function? It should be cumulative distribution function, whatever. These acronyms are hard to remember. But the idea is that this one is cumulative, and we want something that's like point by point, like an individual likelihood kind of thing. And so we just take the derivative of that, and the derivative of x squared is just 2x. And that actually just simplifies. We can get rid of the constants and just say that it's x. Um, why can we do that? Because in a probability density function, the most common probability, the most common probability density function you've seen is a normal distribution. And you're always told like, oh, this is the mean, and this is a standard deviation, and this is the area under the curve, and this is like the probability. The total area is 1, but this area is 30%, and so it's 30% of the population will be between this and this. Okay, that's great, but they never explain what exactly the vertical axis is. And down here it's 0, but up here this could be 1. We could say that the highest point on this normal distribution, we could say that it has a probability of 1. Um, but the normal distribution is like it's a, since it's a probability distribution, it's not a cumulative thing. It's meant to give you the individual probability of a certain point. So if I go like at this point on the normal function, that's supposed to represent this point's likelihood of being chosen. But it doesn't really. You have to take the vertical axis doesn't make any sense on its own for one point. You have to get the vertical axis value for one point and then for another point, and then take the ratio. And that tells you how much more likely this event is than this event. So let's say that, so this is, let's just say that this is a vertical axis value of 1, and this one has a vertical axis value of 0.1. This whole axis could be scaled. This could be 0.2 and this could be 2, as long as it's scaled linearly, because all that matters is the ratio between the 2 points on the probability distribution. This is like a likelihood distribution. Um, so, so that's why I can just scale this. What should be 2x, I can just scale it to 1x, because all that matters is the relative proportions, is the relative likelihood of these different radii. So this radius, a radius that's at point, or here we go, a radius that's at 1 should have twice the likelihood of a radius that's at 1/2. So guessing a point on this ring should have twice the probability of guessing a point on this ring. And all that matters is that ratio. So then it doesn't matter if this is 2x or 1x. 1 over 0.5 is the same thing as 2 over 1. You can just normalize it. But you get to cumulative distribution. You get from cumulative distribution to probability density function by just taking the derivative and then scaling it however you want. So this straight line is the individual likelihood of any radius being chosen relative to any other radius. You just take 2 points and take the ratio. What next? Oh yeah, so we want to generate radii such that this radius, I should go over my mouse because it's kind of hard to see. We should generate radii such that this radius of 1 is twice as likely as this radius of 0.5, right? So we want to generate radius such that like the histogram of their values kind of looks like this. All right. And we can do that by taking the integral of this, which I know we just took the derivative, but we're just taking the integral. That was just kind of to explain. We would take the integral of whatever distribution we want to generate. We would just take the integral of it, and then so I'll just use this x squared from before as the integral. This is the integral of the distribution we want to generate, and then we would just sample at random points along the integral. And there's like kind of an intuitive reasoning for this, which I could explain the intuitive reasoning here for this. But so you would sample points along the integral. Let's do one more. Okay, so you would sample points like that. All right. And you'll notice that there are more points with high. We've taken the we're using the inverse of the integral. So we're treating the y-axis as the input and the x-axis as the output for when we're sampling from the integral. And you'll notice that there are more high values than there are low values. And that makes sense because we want to generate in this histogram here, in this distribution that we want to generate more high values than we do low values. And I could explain a little bit of the intuition for why the inverse of the integral, you sample from the inverse of the integral to get the distribution. Let's say that I had a much simpler distribution, which is, let's say this is 0, and this is 1, this is the x-axis, y-axis. Let's say that I wanted half of my I want to generate a histogram where half of the values are exactly 0.5 and half of the values are exactly 1. Then I would take the cumulative probability, which it would be like a step function. In this case, it would be like bam, 0.5, bam, 1. And if I sampled along the y-axis uniformly, then I would get half of my values as 1 and half of my values as 0.5. And that would generate this distribution here. So you take the cumulative distribution, that's this part, the cumulative distribution, and then you sample along the y-axis, which is the same as taking the inverse, and then sampling along the x-axis. And that would give you the values that generate the histogram that you want to generate. And that's just like a visual understanding of why we take the inverse of the integral and sample from that to get the original distribution that we want. And that intuition, I think, is a big part of understanding this whole process. Um, but yeah, we sample from the inverse of the integral, and that will give us the radius. That would give us the radii. Switch back to mouse here. So we would sample from this distribution, or we would sample from this inverse of the integral, and then that would give us these radii in different likelihoods. It would give us different likelihoods of getting these radii in the correct probabilities that we want. And so that would be our radius of our random point in the circle. So now we've chosen a random radius in the circle, so to speak. And once we've chosen a random radius, then choosing the theta, the angle around the ring, is just you just choose a random point along the ring. You just choose a completely uniform random value for theta because a circle is radially symmetric. And that would give you a random point in the circle. And this like sounds really complicated and it takes me a long time to explain it. But once you have like a visual understanding of, especially this part right here, once you have a visual understanding of this part, of why it's the inverse of the integral, then it's easier to understand the rest of it. Not that I really do, but anyway. And this is what that looks like. This is just bare bones Python stuff. Um, oh yeah, I forgot to actually say that, you know, the integral. So this is the distribution of radius that we want. We want this distribution, this linear distribution. The integral of that is like x squared, and then the inverse of that is square root of x. So we sample from the function square root of x. And so here we generate a random number, and then we sample the function square root of that random number, and then we just choose a random uniform angle, and we do this like a bunch of times, and then plot it on a circle. And that looks like this, which, I mean, it looks uniform, so that's good. And as an example of something that doesn't look uniform, if we, instead of choosing the radius in like the fancy way that we chose it, with sampling the square root of x, if we just choose radius as being a random number from 0 to 1, like uniform random from 0 to 1, then it would look like this, which is clearly uh, not a uniform, distribution over the area of the circle. So I did a terrible job explaining this, but it's really hard to explain it. Okay, give me some slack. So yeah, I think that's it. I don't think there's anything else. And I think the main takeaway here is that, and you really could question the general use case for this. Like why can I not just generate random points in this square and then only choose ones that are in the circle? That's totally fair. Um, but this all kind of just demonstrates a key concept that might help us with other types of problems that are more useful. And the key concept here is that if you want to generate a distribution, you take the inverse of the integral and you sample from it, and then you can get that distribution. So if you sample the square root of x, you get x as a distribution. So you can randomly generate whatever distribution you want. So I could give you kind of an arbitrary function. It could be like, as long as there's no overhangs. It could even be non-continuous, like this one over here was. Could even be non-continuous. But as long as you can take the integral of that, I don't even know what the integral of this would look like. Some whatever. Actually, integrals never go down; they only go up. So whatever, like that, something. And then, so as long as the function that you give me has an integral that can be calculated, and not all functions can. It's actually not very common, but common enough to have a use case, I think. As long as the function you give me has an integral, I can just sample from the inverse of that and reproduce whatever function you gave me as a random variable, which I think is really cool. And I don't know, maybe this could be used to like generate points on the surface of a sphere as well, or other interesting things. Like one interesting thing about what we've been doing with the circle here is you can use it to generate random points on the circle, but you could also use it to create a grid on the circle where each square of the grid has an equal area. So maybe I'll make a new circle for this. Say this is the center. You could make a grid, instead of sampling a random point along the inverse of the integral, you could sample like I wrote down here, you could sample it, periodically in a uniform periodic kind of way. And that would give you something like, oh, this would be hard to draw actually, but it would give you something like this, you know what I mean? And each of these lines corresponds to each of these, to one of the points along here that you sample uniformly. And then you would split it up among the thetas. And the way I draw it is awful, but each of these like shapes would have the same area. And so it's a it's kind of like with like maps and like cartography. You hear about like different maps of, a globe, and it's like you have to choose between two things. It's either directionality is distorted or area is distorted. This would be a projection of the Cartesian coordinates onto whatever this coordinate system is, circular coordinates or whatever. It would be a projection onto this coordinate system that does not distort area. And it does distort direction because this is going left and this is going right. So that it distorts direction, but it wouldn't distort area because the area of each of these would be the same. The area of each of these little slices here would be the same, even though I haven't drawn it like that. Um, but yeah, I don't know. That's that.